Our next topic is vibration and resonance. Many times, vibration always being related and associated with resonance. When we talk about vibrations, many of us will relate it to resonance or high vibrations. So what is resonance and how does it happen? At the end of this video, you shall understand the concept of resonance and differentiate between different sources or root causes of high vibrations. You will then be given an assignment in which you will be applying this concept into 2 case studies and explain the root cause of high vibration in these cases. Let's start with a simple analogy. We learned in Newton's second law that inertial force equal to mass times accelerations. When a mass accelerates or decelerates, there is always a force that acts opposite to the direction of accelerations. This force is called inertial force. It's a vector with the magnitude equals to mass times accelerations, and the direction is always opposite to the accelerations. On the other hand, the force has another relationship to movement. Based on the equations, force is proportional to the movement. If one wants to increase movement, it increases the force. Meanwhile, one can gain high movement when the resistance is low, because movement is inversely proportional to the resistance. In statics, we learned that F equals to kx. Rearranging it, we obtain the displacement is now equals to force over stiffness, in which the stiffness is now acting as the resistance. If one needs to reduce movement, one can increase the stiffness. In dynamics, the inertial force as well as the stiffness force come into play and contribute the overall movement as shown in the equation of motions. Knowing that the accelerations x double dot is equals to negative omega squared x as we discussed earlier, rearranging these equations give the following equation in which it can be written in annotation as follows. Displacement of movement is now equals to force over stiffness minus inertia. So what does it mean? If one needs to reduce movement in this case, one has to look at the stiffness as well as the inertia. In the denominators, getting large resistance restricts the movement. On the other hand, one can also reduce the movement by reducing the force in the numerators. It is not that the stiffness is not a function of omega, but the inertia is. It means the resistance changes over the different frequencies. Let's plot the equation on the graph. When we increase the excitation's frequency omega from small to large values, it's not that the stiffness is constant, as it is not the function of omega, whereas it is shown that the inertia is a quadratic function over omega. Let us now look at when the amplitude x is plotted over the increasing omega. At low frequency, when omega almost equals to 0, the inertial resistance is almost 0. The displacement equations is reduced to as follows. At this instant, the motion is controlled by the stiffness resistance K and is termed as stiffness control conditions. This situation is more towards static conditions, and in this case, the displacement x is in phase or same direction with the force F. When we increase the frequency further, it is not that the stiffness resistance is constant with omega, but as the omega increase, the inertial resistance also increase. It's come to an instant where the inertia cancel the stiffness, which is at this particular point. In these conditions, m omega square equals to k. When we look back at the displacement equations, please note that the denominators is now cancelled to 0. As a result, the excitation force will now act on the mass without any resistance. This will cause the mass to oscillate with large amplitude. If this oscillation is allowed to continue, the amplitude will get larger until it is restricted by damping, non-linearities, or part of the system will break. And in this case, because of no damping, it goes infinity. This condition is termed as resonance. When resonance happens, the system undergoes zero resistance, in which, mathematically, k minus m omega square equals to 0. Rearrange it, we have m omega square equals to k. And finally, we have frequency omega equals to square root k over m. This frequency omega is also termed as the natural frequency omega naught. In other words, we can also say that resonance happens when an excitation frequency omega equals to the natural frequency omega naught of the system. In these conditions, amplitude escalates to infinity or high vibration is usually happen. If the frequency is increased further after resonance, the inertia will overcome the stiffness resistance. The magnitude of oscillation will become small until a point where the motion is controlled by the mass m. In the displacement equations, we can see that the denominator is dominated by the inertias or controlled by mass. This is termed as mass control conditions. The system is said to be in isolations. In this case, the displacement x is out of phase or x opposite direction with the force. What we have discussed just now was on a system without damping. The displacement escalates to infinity. When we deal with system with damping, in which most of the system in real life do come with some sort of damping in nature, another resistance to motions come into play. For instance, the damper. Damping is also known as an energy dissipator. In free vibrations, a system without damping will continue to vibrate constantly, whereas a system with damping will decay over time because the energy is dissipated from the system through damping. Let's look at the equation of motions when damping force Cx dot is included. The solution of this equation gives the displacement as follows. And when we compare with the displacement equation of undamped vibration we derived earlier on, we can see that addition damping resistance is at the denominators of the equations, acting as an extra resistance to the system. A system with damping, even at resonance, when the stiffness and inertial resistance cancel off each other, the presence of damping provides the resistance that prevents the amplitude from escalating to infinity. We can conclude that amplitude of vibration at resonance depends on the amount of damping. Higher damping gives lower vibration at resonance. We can also say that damping of a system is important to know when we deal with resonance. So, by now you should understand what is resonance and how does it happen. In summary, it's note that resonance or high vibration happen when the system resistance is low, in which stiffness cancels off inertia, giving low denominator in the displacement equations. On the other hand, High vibration can also happen when the system's force is high, leading to large numerator in the displacement equation. So for the first assignment, please watch the two videos given and discuss how did they happen based on vibration point of view. Submit an individual report on this.